Thanks for the introduction. So hi, good afternoon, everyone. Today, I will not just present yet another file system for non-volatile memory. Instead, I'm going to tell you an architecture called Diyu that enables high performance and security for a wide range of Userspace NVM file systems. So with Diyu, we aim to design the right file system for emerging non-volatile memory devices, such as Intel Optane persistent memory and the future CXL-based ones. And since software can access NVM directly from the user space through the ordinary load and store instruction, this has motivated prior work on designing the libfs architecture, where most of the file system functionalities is moved from the kernel to an application-linked library. And the libfs is an ideal fit for NVM, because NVM has extremely low access latency in the scale of hundreds of nanoseconds. And as a result, any software overhead must be minimized. libfs allows applications to bypass the OS and directly access NVM, thereby eliminating various overhead incurred by the OS. In addition, libfs enables customization. A conventional file system aims to provide acceptable performance under all scenarios. And with the extremely high performance of NVM, we hypothesize that designing such a generic file system is challenging. libfs allows applications to customize libfs based on application workloads, and thereby fully exploiting NVM performance. And in addition, libfs has unique advantages with respect to customization. First, since all the libfs is in the user space, application does not require any special privilege to perform the customization. And as a result, all the applications in the system can benefit from it. In addition, the conventional file system faces the challenge that customization optimizing performance for one application may slow down another. And the libfs can effectively avoid this problem by making each libfs private to an application. However, a key challenge libfs must overcome is to ensure secure sharing. While the operating system and the hardware is trusted, the user space application and the libfs can be potentially malicious and attack others by corrupting the shared state in the OS or NVM. So to prevent such attack, a libfs must first enforce file access permission. And achieving this is easy because the libfs can offload the permission check to the hardware MMU. In addition, file system relies on certain invariants to function. As one example, the directory hierarchy must be a connected tree. There cannot be loops or disconnected files. And achieving this requires a trusted entity, either the kernel or user space privilege process, to validate the invariants. And this is the main challenge to achieve secure sharing. So can we design libfs that maximize the degree of direct access, supports unprivileged and private customization, while also enable secure sharing among potentially malicious applications? Achieving these design goals is a challenge because there are inherent tensions among them. First, with direct access, application can bypass the kernel and the associated protection to directly access NVM and corrupt the file system. Since the kernel is not on the critical path, it cannot prevent such attack. And this raises the question, when should the trusted entity validate the metadata invariants? In addition, with customization, each libfs has a different data structure optimized for its application. However, the trusted entity does not understand the semantics of this data structure. And this raises the question, how to validate the invariants given customized libfs? So existing work fails to resolve these inherent tensions. So one class of design allows libfs to directly access NVM for data operations. However, any metadata update operation that may potentially corrupt the file system is first sent to a trusted entity. The trusted entity validates the operation and then performs it. While this design ensures secure sharing, it does not fully achieve direct access, since metadata updates are mediated. Furthermore, since the trusted entity needs to perform the update, it must implement part of the file system functionalities. And this prevents unprivileged and private customization. Since now, customization may involve changing the trusted entity, and this may require special privilege and affects all the applications in the system. And another class of design shares the libFS among all the applications and allows libFS to directly access NVM for all file system operations. However, this design is vulnerable to attacks. And as a result, this design either assumes applications are trusted or they include some mechanism to mitigate the effects of an attack. And this design also does not support private customization since libFS changes affects all the applications sharing it. So why do prior design have these disadvantages? We believe the root cause lies in the approach they use to maintain the conventional file system abstraction, which requires all the applications in the system share the file system simultaneously. And as a result, existing design either use a trusted entity or use a libFS to maintain the whole file system state. And this design choice is the root cause on why existing design cannot simultaneously achieve all the desired properties. So to overcome this issue, with Diyu, we consider how to partition the file system state. And our key insight is that the file system state can be partitioned into core state and auxiliary state. Core state is the state that is essential for file system integrity and functionality. It must not be lost, since it cannot recover from any other state. While auxiliary state is used by the file system to implement supplementary functionalities, such as caching. Auxiliary state can be discarded and rebuilt from the core state. So as one example, in a typical file system, the file access permissions, directory entries, and the file contents, they belong to the core state. They are essential for correctness and must not be lost. While state in file descriptors, caches, locks, and bitmaps, they belong to the auxiliary state. They are used to implement supplementary functionalities and can be rebuilt from the core state. So with the insight of state partitioning, meeting all the design goals becomes significantly easier, since we can use the core state for secure sharing, and we can use the auxiliary state for performance purpose. So based on the state partitioning, Diyu has three components: a libFS that provides file system functionalities to the above application, a kernel controller that enforces access permission, and also a verifier runs in a user space as a privileged process to validate the invariance. And we call this architecture Diyu because it cleanly decouples the responsibilities of a conventional file system into three components. Each component performs a different task, and they work in concert to form a beautiful musical composition. So a file system based on Diyu must first define the layout and the data structure of the core state, and then share it as common knowledge among all the components. And that is also the low-level abstraction exposed to libFS to build a high-level file system abstractions. And each component has its own private auxiliary state. A component cannot change the layout and the data structure of the core state, but they are free to do so with their auxiliary state. So how does state partitioning enable Diyu to meet all the design goals? So for direct access, when a libFS first accesses a file, it sends a request to the kernel controller to ask for the core state of the file. The kernel controller then programs the MMU and maps the file's core state into libFS address space. The libFS then builds the auxiliary state of the file from the core state and can directly access it afterwards. And for unprivileged and private customization, since only libFS implements the file system functionality, and also libFS is private to an application, and as a result, application can freely customize the libFS by modifying the auxiliary state without requiring special privileges or affecting others, and thereby maximizing the benefits of customization. And state partitioning also enables Trio to resolve the design tensions involving secure sharing. So for the first issue, Trio allows either concurrent read or exclusive write access to a file. And as a result, Trio can prevent attacks by validating the invariance only upon sharing a modified file from one application to another. And for the second issue, the verifier can perform the validation since it understands the core state, the data structure of the core state. And it only needs to validate the core state since the auxiliary state can be rebuilt from the core state. So most basically, upon file sharing, the libfs discards the file's auxiliary state and then unmaps the core state. The kernel controller then passes the core state of the file to the verifier for verification. If there is a corruption, the verifier will inform the kernel controller to fix it. And once there is no corruption, the file's core state is mapped to the libfs address space. The other libff then builds the file's auxiliary state from the core state and can then securely access the file. So based on Trio, we designed ArcFS, which implements the POSIX APIs, but not exactly the same POSIX semantics. So there are many interesting design aspects of ArcFS, and due to time limitation, let's focus on how to design the core and auxiliary state. So we designed ArcFS core state as simple as possible to maximize the degree of customization while also minimize the validation overhead. So most basically, ArcFS core state has a super block that stores general file system information, a shadow inode table that stores file access permissions, and file pages that stores content of files and directories. So within a file page, each file consists of a set of index pages and data pages, and each entry in an index page points to a data page. And the data page stores contents of regular file or directory entries. While the auxiliary state can be used for various performance purposes, in ArcFS, we choose to design it to maximize the multi-core scalability. And for that, ArcFS employs scalable data structures, such as a Redis tree, to index a file, and an efficient concurrent hash table to index a directory. And furthermore, ArcFS extends the conventional design by maintaining multiple login tails. Each data page in a directory has a login tail. And finally, ArcFS uses fine-grained locking to minimize the contention. And based on ArcFS core state, we designed a libfs customized for small files, kvfs. To access a file, the conventional POSIX interfaces requires an open, a read, and a close. This involves 3 system calls and the associated overhead of maintaining file descriptor, which is too high for small files. And with kvfs, it eliminates such overhead by replacing the POSIX interfaces with a get and set interface. And we evaluate Trio to answer the question, does Trio improve NVM file system performance? And we compare Trio-based file systems against Nova, which represents kernel file system, and SplitFS, which represents file system that mediates metadata updates. And this slide shows the results of the basic file system operations. The y-axis is the throughput, and the orange bar here is ArcFS. For data operations, ArcFS performs similarly to SplitFS, since both of them allow direct access for data operations, and it's 12% faster than Nova. And ArcFS is the only one that supports direct access for metadata operations, and as a result, significantly outperforming others. So in summary, the direct access enabled by Trio maximizes NVM file system performance. And this slide shows the scalability of metadata operations. So we use 2 representative workloads, web proxy, which is a read-intensive one, and warmail, which is a write-intensive one. And for both workloads, ArcFS outperforms others. For others, throughput stops increasing after 8 threads due to a scalability bottleneck in the kernel VFS layer, while ArcFS continues to increase linearly. So in summary, Trio enables scalability by bypassing the existing bottleneck in the kernel. And this slide shows that the customized file system, KVFS, can further outperform ArcFS in the workload it targets. So in summary, customization enabled by Diyu can further improve performance. So to summarize, library file system have the potential to fully exploit NVM performance by enabling direct access and unprivileged and private customization. However, these performance advantages poses a significant challenge on securely sharing the file system among potentially malicious applications. We present Diyu. The key insight of Diyu is to partition the file system state into core state and auxiliary state. Core state is the essential state for file system correctness, is shared among all the components and is used for security, while the auxiliary state can be rebuilt from the core state, is private, and is used for performance, and thereby simultaneously achieving all the three desired properties. Diyu is publicly available here, and I hope you folks enjoy using it. With that, thank you for your attention, and I'm glad to take questions.
First question on my right.
Yeah, hi, I'm Sarah McAllister from CMU. Thanks for the talk, it was really good.
Thank you.
What type of customizations, like, generally are you interested in? I know you had the one example of small files with a key value interface, but what other customizations do you think people are going to use this kind of interface for?
So in the paper, we have one more example where actually we replace the per directory hash table into a global hash table so that this eliminates the overhead of path resolution. So these are like, in general, we consider that if you design a minimal core state, we hypothesize that you can customize lots of things. For example, the interfaces, the algorithm, like caching algorithm, locking algorithm, or even, for example, the design of some key data structures.
Thanks.
You're welcome.
In the middle.
Hello, KIT Karlsruhe, Peter Maucher. Can you explain a little bit the differences to ARI from Userspace a few years ago, because your design seems pretty similar?
Right. Thanks for the question. And I think the key difference is here. So this, I believe, is exactly the architecture ARI is using. So it needs to mediate metadata update operations, and as a result, the trusted entity needs to implement part of the file system functionalities. And this kind of coupling is the reason why they cannot fully achieve all the three design goals, while Diyu tries to reconcile these design goals and find another middle ground.
Thank you.
Thank you. And last question on my left.
Jerry from University of British Columbia. Really interesting design, and wonder whether this architecture can be applied to other storage media and building application-specific file system.
Thank you for the question. So in the paper, we have a section where we assume our assumptions on hardware, and presumably we believe this assumption does not really apply to NVM. We just implement on top of NVM, but we believe can be applied to future hardware. And actually, I think our lab is actually actively exploring whether this can be extended to other storage media.
Thank you so much.
Thank you. Let's thank our speaker.